This is exercise 1.56 in your textbook, using a XY set of axes. So we have the vector A, which is in the first quadrant. We have the vector B, which is in the second quadrant. And the vector C, which is in the third quadrant. Not doing a good job of drawing these to scale, I'm afraid. That angle there is 53 degrees. This angle between the B vector and the positive y-axis is 30 degrees. And the angle between the A vector and the x-axis is also 30 degrees. So the magnitude of the A vector, so you can either write it with the A with the arrow and then the two vertical lines, or you can say that's just A. A has a magnitude of 100. B has a magnitude of 80. And the C vector has a magnitude of 40. And what the question says is we want to find a fourth vector. So we're going to find a vector, we're going to call it the vector D. So we're trying to figure out that vector D such that if we add all the vectors together, so we add the vector A plus the vector B plus the vector C plus the vector D, we add everything together and it ends up equaling 0. And you don't have to do this unless your other instructor makes you, but technically you should make that the 0 vector as opposed to the scalar 0. But anyway, to start this, what I'm going to do is I'm going to make use of components. So what I want to do is I want to start with the x component of the A vector. So I'm going to write that as A sub x. And looking at the way that this is drawn here in the 30-degree angle, the 30-degree angle is associated with the horizontal component of the A vector, so that's cosine. So this is going to equal A, meaning the magnitude of A, times the cosine of the angle. And the book likes to use something like theta sub A as the subscript. So I would write that out as 100 times the cosine of 30 degrees. And I'm just going to write this with 3 sig figs here. 86.6. I'm going to do all the horizontal components first. The B vector, so if I look at this, I can see that it points to the left, which means it's going to end up being negative. I'm going to stick with the notation that the book uses. So I'm going to say it's going to be B times the cosine of this angle, and the angle is going to be measured from the positive x-axis. So the magnitude of B is 80, and the angle is actually 30 degrees plus the 90 degrees, because we need to go between positive x to positive y-axis, which is 90, and then another 30 degrees. So this ends up being 80 times the cosine of 120, which is going to be minus 40. And C of x is going to be the magnitude, which is 40. It's going to be the cosine of 53 degrees plus 180 degrees, because we're having to measure counterclockwise. And so that's 223 degrees. And when we plug that in the calculator, we get negative 24.1. Now we can do the same thing for the vertical components, A sub y. So A sub y is going to be A times the sine of theta sub A. So that's 100 times the sine of 30 degrees. So that's going to be 50. Again, I'm not writing sig figs here. I'm just doing the math. B sub y is going to be 80 times the sine of 120 degrees. That's going to end up being 69.3. And C sub y is 40 times the sine of 223 degrees, which is minus 31.9. Actually, I just noticed 69.3 is not a degree, it's just a value. Okay, just as a quick aside, for example, let's look at the c vector here. The way I typically do this actually is I would look at this and I would say, okay, let's say I want to get the x component, c sub x. I know it's going to be negative because it's pointing to the left, and then I could look at the way that this is drawn and I could say, well, that's the 53 degrees is in the adjacent side, so that's going to be minus 40 times the cosine of 53 degrees. And that will give you the same thing as the negative 24.1. But if you do it this way, the way I just showed you, you have to keep track of the signs, the SIGN signs. And if you use the standard angle measured from the positive x-axis going counterclockwise, then all the SIGN signs take care of themselves. Okay, so all that is done. Now we can basically go back to our original equation here. So if I say a plus b plus c plus d equals 0 as a vector equation, if I want to, I can now solve that for the vector d. So I can say that the vector d is going to be equal to negative the quantity of a plus b plus c, all vectors. So that's going to be negative. And now I'm going to break this out into components. So I will say that's negative a sub x, and I'm going to use the unit vectors here. So a sub xi plus a sub yj, that's the a vector, plus b sub xi plus b sub yj, that's the b vector, plus c sub xi plus c sub yj, that's the c vector. So then what we can do is we can group these according to like unit vectors. So if we group all the I vectors together, I'm going to still have my negative sign out in front. So I'm going to have my bracket a sub x for the a sub xi plus b sub x plus c sub x, and that's all in the I direction. And then I'm going to group all the y terms together. A sub y plus b sub y plus c sub y. That's all in the j direction. Okay, now we can actually start plugging in our numbers. So a sub x is 86.6 plus b sub x. Well, b sub x is negative 40, so I have to put a negative 40 there, plus c sub x, which is negative 24.1. That's all in the I direction. Then in the y direction, we have a sub y, which is 50, plus 69.3, minus 31.9, close parentheses, j, close the brackets. Just another quick note here. The standard notation is you put a little hat over the I and the j to signify that those are unit vectors, as opposed to the arrows over the letters that represent general vectors, although I think people would understand what you meant. But normally unit vectors have these little hats on them. That's the official term hat, and regular vectors have the arrows on them. So moving this vector d up here to make some more room, I can just plug these numbers into a calculator. So 86.6 minus 40 minus 24.1 is 22.5. And 50 plus 69.3 minus 31.9 is 87.4. So carrying through now, my d vector is going to equal, I got to remember the negative sign, negative 22.5 in the x direction, so it gets multiplied by this I unit vector, and then I still need the negative sign, minus 87.4 in the j direction. Now if I wanted to figure out the magnitude of the vector d, that's just going to be the square root of the sum of the squares. So square root of 22.5 squared plus 87.4 squared. Notice that the negative sign doesn't really matter because you're squaring it, so square of a negative is positive, so it doesn't really matter. So you carry that out, you end up getting 90.2. And I actually haven't mentioned this, but in this problem, these are all forces, so that has a unit of Newton. So I probably should have been putting those units on there, so it's 90.2 newtons. Now, if I want to calculate an angle, I find it helpful sometimes to kind of redraw this picture here with the axes. So here's my x and y axes. So I look at D. D has a negative x component and a negative y component. So it's going to be a vector pointing down and to the left. So it is in the third quadrant. And there's lots of different ways we can do the trig on this now because we know basically the two sides of a number of different right triangles. So, for example, if we wanted to, I could draw a right triangle like this, where this one side is 87.4 and the other side is 22.5. So that would correspond to the right triangle, to one of these right triangles here. I could also draw the other side of it. So I could draw a right triangle like this. This would be 22.5. This would be 87.4. So sometimes it's helpful to do that, and then you can calculate your angles based off of that. I'm going to delete those. What I'm going to do instead is I will just stick with what I've been doing before. So I'm going to measure an angle counterclockwise from the positive x-axis, and that angle is called theta sub d. Okay, so now to find this angle theta d, equation 1.7 in your textbook says that we can relate the angle to the tangent. So what it's saying basically is that the tangent of, let's say in this case theta sub d, is going to be the y component divided by the x component, which in this case is going to be negative 87.4 divided by negative 22.5. And when you do the arctangent, or the inverse tangent of this quantity, which is 3.90, you get 75.6 degrees. But we have to remember, especially looking at this image here, well, 75.6 degrees would be in the first quadrant, that with the tangent we have to do a plus or minus 180 degrees. And so if we add 180 degrees to 75.6, that puts us into the third quadrant. So for us, for our value for theta sub d is going to be 75.6 plus 180, which is 255.6, or rounding to 3 sig figs, 256 degrees. So we have a magnitude of 90.2 newtons, and the angle is 256 degrees as measured counterclockwise from the positive x-axis. Now, as a side, if you were to try to use any of the equations like d sub x is equal to d cosine theta d, if you were to try to then use inverse cosine of this, you're going to have to, it's a little trickier. So the recommendation is to either use the tangent like this, or else, like I showed before, you can draw the actual triangles out and just do the trig off of a right triangle, and then keep in mind how that fits into your axes.